Hello, everyone. Welcome to Amitrek's technical presentation. Today, we're going to talk about photovoltaic panels, understanding the fire hazard theory. This will be a technical video. It's important to understand that the information contained in this presentation might be boring to some people, not too technical inclined. The reason why I selected this presentation is because the number of losses in the industry due to photovoltaic panels have been increasing, and they will keep increasing due to the installation, due to also to thermal degradation, and also over time degradation of the elements. That's important to understand. But before we start, I'm just going to point out some causes of photovoltaic panel fires. First of all, panels not approved as a system. It's important to understand that the photovoltaic panels should be part of the roof cover system. They must be selected, at the same time, or if there's already a existing installation, the engineer should evaluate the roof, understand the assembly of the roof cover in order to determine whether whether photovoltaic panels can be installed or should be avoided, or maybe just look for another area. Panel manufacturing not meeting safety and security standards. That's basically not approved panels. Okay. Improper installation. That is a very critical cause of fires due to unqualified contractors. Damaged panels due to mechanical and cracks. Damaged panels due to natural hazards. For example, hail, snow, windstorm, and also earthquake. Damaged bypass diodes. That's also an important cause. We will see that. And also bypass diode modules. We will understand why are those two important. Thermal degradation and overtime degradation, they basically go hand by hand due to the overtime, uh, you know, overheating the panel due to the sun, due to other issues, that will degrade the components, and eventually they can arc the electrical cables. Lightning strikes, electrical cables, electrical connectors. Those two are that's probably also on the high causes of fires, electrical cables and electrical connectors. Moisture, very, very critical. Moisture, and that goes in with the thermal degradation and overtime degradation, because once you have degradation, eventually you will have moisture inside components, inside the panel, and you will have hot spots due to high resistance and connectors, or maybe on cables as well. Combustible or old roofs, like that's pretty much also very similar to number one. Inadequate roof selection. Again, the roof should be selected or should be evaluated to determine whether panels can be installed. If there's no information, the best recommendation is not to install panels until the information on the roof are available and evaluated, of course. Inadequate maintenance, very high reason of fires. That's the you will see today, especially on the shading effect and other causes as well. And this is a picture of a panel. These are the general components, basically 4 or 5 parts. This is the template glass, polymer sheet, photovoltaic cell, backing material. Those are the main components of a photovoltaic panel. Shading is something that we should understand a little bit more clearly, because once it's blocked, the photovoltaic panel, if it's blocked, if it has a shadow effect due to many causes, that will be called shading. The shading will obstruct and will decrease the amount of sunlight received by the panel, and obviously that will be a decrease of the current by that specific panel or by part of that panel as well, and that will create a problem. And conditions that create shading We have trees, as you can see here in the picture, equipment, buildings, and walls as well. Sometimes during the day, the sun rays can be, parallel or perpendicular, on the panels, and that should not be a problem. But once the sun start moving, then we can have some shadows over the panels, and that will create some problems if we don't have certain equipment. Dust as well. Many factories are located in dusty areas, and that will eventually cover the panels, and that will decrease the current of the panels, and that will also can create some hot spots due to dust. And bird droppings, very popular and very common as well to find out and to find panels like this in installation, especially on wooden areas. Hail damage and crack panels. Okay. Those shadings can create and will probably create some hotspots, and that will be an ignition source. The ignition source will create fires. As you can see here in this picture, you can see the rooftop fires, especially the area, difficult to fight, especially manually fighting these panels. Requires to have aisles, requires to have some access to all areas of the roof, because right now there are a lot of industries and companies that are installing photovoltaic panels throughout the roof without leaving any kind of aisles in between. And there will, that's pretty much extremely difficult to manually fight the fire. So the outcome will be the fire will just propagate throughout the roof. And if the roof's not properly selected, the fire will go inside the building and then just have a total loss. Okay, we're going to start with the basic theory. First of all, what is a photovoltaic cell? Okay, I'm just going to go to the unit, the cell by itself. First of all, we should understand that a photovoltaic cell, it's a semiconductor. It is not an electrical device. It's a semiconductor, and it's manufactured by basically two materials. One is it's called the P substrate, which could be right here. That this would be the P substrate. Then there is the other side, which is the N substrate. So this is a silicon material, and the P substrate is it's basically a crystal, and it's doped with impurities that it will make the semiconductor with more holes. Okay, holes will be some carriers, positive carriers, and on the other side of the substrate we have the N type, and that's the one that also it's doped. It's a silicon doped with excess of electrons. Okay, so you have more electrons on one side and more holes on the other side. And in the middle, you will have a depletion layer right here, which will have, this will be the barrier. Okay, and on the top, you also have some at the bottom, you have the base, okay, which is the connector where it will be connecting the terminals. This is a picture. This is a picture of a diode. It's not of a cell, but for just to explain how that works, I have it in here. When the diode, the positive terminal, which is this one, and the negative terminal are properly connected, the positive to the P region or to the P substrate. This is the N substrate, the N region. If we connect the positive, all the holes will be going on this direction, okay, this direction, and the electrons will go to this direction. So the holes will try to move and occupy a hole. But first of all, there will be a depletion region on that one, and that will create a voltage barrier between those two materials. And this is called a forward biased diode. It's connected. The polarity, it's the plus on the P region and the negative on the N region. Or in other words, the positive terminal, it's connected to the anode, and the negative to the cathode. Now we reverse those terminals. We have this drawing. We have now the negative terminal connected to the P substrate, to the anode, and the positive terminal to the N substrate, to the cathode. Okay, once we have this, we will increase the depletion region of the semiconductor, of the diode. And this will be reverse biased. We will have a very, very small current, and that will be a leakage current. That's in the range of the microamps, very small, until we reach a certain level of a reverse voltage that we will see in a curve to so you will understand it. But this is how it's connected on the reverse biased. Now, these three curves, they're pretty much the same. The only difference between these three is the amount of light that is received by the cell. This is a high intensity light, and then it's a middle, and this is a low intensity light. This could probably think that this is once when you have a shade, you would reduce the amount of current. So you're probably going to move into the upper curve. If you have there's no obstruction, probably you're going to have the bottom curve. So let's focus about that right now, just for explanation purposes, on the top curve. And you will see that when you have a forward bias, you're working on these two quadrants. Okay, you have the positive voltage right here in the terminal, and also into and the negative into the end substrate. That will have a forward bias, and that's pretty much this drawing over here. Okay, so that you will have current flow going through the diode, or in this case through the cell. Now, if I reverse the polarity of the or the terminal connections, then I will go into the negative. Then I will make negative the P region, or the anode, and the positive the cathode. Okay, if I have that, I will go, and this will be this is a current, because I'm on the Y, on the X and the Y axis. Then I have a very small amount of current called the leakage current. And like I said before, this is in the range of microamps. But once I reach a level of a voltage, this is called a breakdown voltage, and then it will just go very fast, and we have a lot of current. Okay, even when it's on the reverse biased. Okay, so this is the curve of a diode, and we should understand. Many people confuse that a diode, it's similar to a check valve, but it's not a check valve. Okay, it's not a check valve because it's a semiconductor, and we have leakage current when you have reversed polarity on the diode or in the cell. I'm going to show you here, this is a picture of a physical diode, okay? And this is a module of a bypass diode, or bypass diodes, for a photovoltaic panel. And this is a typical arrangement of different panels. Okay, we have 4 panels over here, and the green diodes, this is external diodes, okay? These diodes will be these diodes. Okay, these green diodes are called the bypass diodes. They could be located below the panels, or away from the panels. These two over here, they're called blocking diodes, and this is just to avoid the if we have any kind of inverse current damaging the panels, this will avoid that to happen. Okay, but this is the arrangement. Now, before we start the analysis of the elements, we should be familiar with the symbols. We can use these two symbols to represent a photovoltaic cell, the unit, not the panel, just the cell. A panel is made out of many cells, and this will be the model of a cell, of a photovoltaic cell, which has two elements. This circle over here with an arrow, this is a current supply, okay? Not a voltage supply. This is a current supply. And this is a diode. So this will represent, will model a photovoltaic cell. These here are representing the sun rays, received by the cell. Okay, and this is again a curve, just a simplified curve. You will have here the forward region, and just pay attention that it depends on the diode. Could be 0.56, 0.6, 0.7 volts, just to have a forward biased diode and start increasing your current. If you have, like, for example, 0.1, you're not going to have any current. Okay, this is important to understand as well. Now, if I go on the negative side, on the negative and the x-axis on the volts, once I invert the polarity of the diode, then I will be on these two quadrants. Now, this is the leakage current area, very, very, very small amount of current, microamps. And once I reach, this is the breakdown voltage point, and then I have a lot of current, okay, over here, boom. I thought this will be the reverse region, and this is the reverse biased, or with inverse polarity, the anode with the negative, the cathode with the positive. And for the forward biased, it's the anode with the positive and the cathode with the negative, okay? When I'm over here, just pay attention about this. This will be the maximum current that is very close or almost the same as a short circuit current, okay? So the short circuit current will be equivalent to the maximum current of a cell. So that's, you could say that all cells will operate where they're not blocked with the short circuit current. We're going to analyze a closed circuit and a open circuit. When I have a closed circuit and I only have the cells like this, okay, this is my load on this one, so I don't have bypass diodes in my circuit. Then this is the curve. When there's both cells, I'm going to explain with two cells only. Both cells receive the same amount of sunlight. Then they will both have the same amount of current produced by the current supply of the cell inside the cell. So this current will be a short circuit condition, which I might mention over here. And I will have a short circuit. If I have a short circuit between these 2 points, my voltage between these 2 points is equal to 0. That is why this diode, internal diode, it's not operating. Okay, then I have the current going through the load. Okay, then we close the circuit, and then passes through the other cell, and I have the same situation. I have the short circuit current over here, 0 voltage on the diode, and this is open and pretty much on the open condition, 0. Then this will be this curve. I have one curve and I have the other curve. If I had more cells, that would be this red, for example, right here it says 9 unshaded cells. Okay, I'm assuming that this will be equivalent like to have 9, and this is only 1. The total amount of current will be the addition of these two curves, which gives me this black curve. Okay, so I add this to this, then I have this curve over here. Okay, and you will see that if I have current going through the cell, I'll have the cell will heat up a little bit because of current going through the panel. So right now, my panel will start heating up. All right, so what happens with there's, for example, a cloud, or there are some tree shadows, bird droppings, dust in some areas of the panels or in one full panel, then I will have this situation. I'm representing that, and I decrease the amount of sun rays received by the cell, and this is the same. When I have this situation, my current, it will no longer be the same on both cells. So that will be unbalanced. Okay. And when I have this unbalanced condition, I will create a voltage drop, a positive on this side and a negative on the other side. So I will have this diode on the forward biased mode. That means that I will have current going outside the cell and also inside the cells through the diode. That will increase the temperature of the photovoltaic panel. So I'm putting over here with more. But on the other side, on the other cell, the once I receive less sunlight over this cell, the current will decrease. Okay, that decrease over here, that's why I have this polarity, the plus and the minus. That's why this is inverted, this operates. But I'm going to be on this side of the curve now. It's going to be inverse with inverse polarity. It's going to be a reverse biased mode that's going to go this way. And if this can reach very quickly, and this will start increasing the current on this direction, it's in the microamps range, and I will reach very quickly their breakdown voltage. Once I reach the breakdown voltage, I will have a current going against the flow of the diode on the inverse mode. Okay, basically what that happens is that the barrier will be broken, and then I will have a current of electrons going through the diode. Okay, that will damage the diode, of course, and I will have more current over here, and that will increase the temperature of the cell. Okay, very rapidly, because this will be very, I'm not going to be like, for example, here in this current, I'm going to have a lot of negative current going the other way, but it's going to have more than on the other side. So that will increase, and it will increase as well as this one, because it's on they're connected in series, and these two will increase the temperature. But this cell will be on a higher temperature. Okay. Now, if I see the curves, important to know, this will be like, again, that red curve, and this is my shaded cell. It's lower because because it's shaded and the current is less. So right now, since I'm working on the negative side, this represents the amount of power that has to be dissipated through the shaded cell. Okay, so you will see this is the amount of power, and this is how much of heat is going to start to dissipate on that one. So the panel will heat up. Now, if I add those two curves, the red one and the blue one, I will have the final curve, which is this one. Okay, so that will be this current over here. Okay, if I have this current over here at the end, you will see a decrease of performance of the panel. Okay, and this is without bypass diode. So my problem now is on this situation. What do I do to avoid my cell from heating up during a shading event? Okay, so that's why I'm writing here, the cell will heat up and this will cause a fire. All right, so now I go and move to the closed circuit, same situation, but installing a bypass diode or bypass diodes for every cell. So I install these two diodes. Okay, they are inversed. Okay, so right now it's a short circuit. It's the same situation. Since this is they receive both cells of all cells receive the same amount of sun rays. They will produce the same amount of current. Same amount of current. They have the short circuit situation. So these has a 0 volt, and that's why none of these two diodes operate. Okay, and the panels will heat up normally. It's a normal temperature for the all normal operating temperature for the panel. Okay, so like I say here, neither diode, cell, or bypass is operating. Okay, so then I have the same curve. All right, because they're exactly the same situation. So I have the red curve, and the blue curve. You add them together, then you have the black curve. Okay, this will be the addition. Okay, so it's the same situation. You have matched currents, voltage across the cells, an internal diode is 0 because of this is a short circuit current. And we move now into the situation that we had the problem. We have a shading issue on one of the cells, or one or partial on the panel. So right now, once I have the same situation, as you remember, that will create a positive side over here and a negative. Then in order to avoid going into this area of the curve, by adding the bypass diode, I'm going to force the current to go through the diode. So once I start having positive, and as soon as it reaches like 0.6 volts, more or less over here, then this one will operate. Then it will be, since this is in reverse mode, this will be the curve, because this is inverted. And if I reverse it, I end up on this mode and on this quadrant. So this, since this is on the forward biased mode right now, this will cause the current to flow through the diode and then to the other part, to the other cells. Now the curve of that diode we eliminate. If you remember, this will be my curve of the current supply. Then if I add the bypass diode, I will replace that curve by the diode curve. But since this is inverted, I will just rotate this on the y-axis. So this is why I have this side of the curve of this side of this axis, and this one over here will be this over here. Okay. So then this will take all the current. I will avoid this shaded cells from heating up. So you will see it will not heat up. It will heat up the diode, but not the cell. Okay. And the output, the combined curve will be the addition of the red curve, which are these cells or this cell, and the addition of this blue curve, which is going to be the bottom cell. Okay. Now, if I add them together, this will be my final curve. You will see that it's not the same, but at least it's very close to the original one. That is when you don't have the shadow effect on one of the cells. Now, the other important thing is this, that the area below the curve, like we looked before, that corresponds to the power that has to be dissipated through the cell. So this will be this yellow area of the curve. So it's reduced significantly. And the yellow part now, this is the power has to be dissipated through the diode, through the bypass diode. Okay. So this is an improvement of the system just by adding those bypass diodes. Okay. This is what I'm writing here. The power dissipated in the cell is considerably reduced. The risk of panel fire is reduced as well. Number two, the combined curve is significantly improved. In other words, it is a slightly smaller than the combined curve when no shading is used in a cell. Therefore, the power delivered by the cell is very similar to the unshaded curve. And that can be observed in these two curves. This is the curve that we had before with no bypass, and this was on the shaded. Okay, this is the area on this under this curve, and this again, this corresponds to the amount of power that has to be dissipated through the panel. That's a lot. And this, by adding that bypass diode, I only have this small area, so that's a big improvement. Okay, now what happens when you have an open circuit? A lot of people think that there's no flow in the circuit. There's no flow in the circuit, but there is flow inside the cell. Okay, that's why we stopped the circulation over here. This is the switch. It's open. Both for this example, both cells receive the same amount of light. The sun rays, they are the same. Okay, so we have the same current going into here. So this is a short circuit current. Comparing when the circuit is it's closed. On the other, remember that there was no current going through the internal diode. If you open the circuit, you will have current inside the internal diode, and this will be the short circuit current. So this will heat up, comparing the other situation, more than the when it was with the closed circuit. So again, that happens on all the cells. In this case, from the top cells and this bottom cell. Okay, and see here that both cells have their diodes on their forward bias mode, and they will allow, obviously, like I'm indicating here, flow current through the cells. Okay, but pay attention over here. Like I'm going to repeat this. This is an open circuit, and I have current. I have current inside inside each cell, and they will heat up. So it's a misunderstanding that people say, I'm just going to disconnect it and nothing's going to happen. And suddenly you have a fire. So it's very critical to understand this. Now, for an open circuit, what happens? You have an open circuit when you have bypass diodes. Okay. When you have open circuit and bypass diodes, and you have the same amount of sun rays received by the cells, you have the same situation, because you have the like before, you have the current going this direction, because this is the polarity of the plus. It's on the anode and the negatives on the cathode. So this is forward biased, and this diode is inverse biased. Okay, this is the plus, and this is a minus. So this is on this side of the curve. Okay, this on this side. So this situation, we have the matched current in each cell, and this will be a short circuit current. Okay, and neither of these two bypass diodes are operating. Okay, now I have a shading situation. There's a cloud or something that will obstruct part of or sections of the panel. Then have less sunlight received by this cell. That will reduce the amount of current. Okay, this will reduce the amount of current, and in comparing with this will keep having the same amount of current. This will heat up more than this in a open circuit. Okay. And this causes the current generated by the cell to be lower and to circulate internally within the cell. Neither of the bypass diodes, okay, as you can see here, because this is a plus, a minus, plus, minus. This is in the reverse. Those two are in reverse mode. They will not operate. Okay, so that's pretty much all the examples that I want to show you. Now, some recommendations to improve, for just to keep in mind, just to decrease the number of losses for photovoltaic panels. One is to conduct an assessment by an experienced personnel. Regular visual inspections, okay, especially to not just to find out and to identify if they are damaged, if there are something that will block the panels and create a shadow effect or shading. Regular maintenance, cleaning. We have to clean those. All the panels have to be cleaned regularly because that will reduce. And as you can see, you can even, because if they're dirty, you can have some, not the dirty ones, the other ones, the other panels not dirty. When they're in the open circuit, then those will be heat up. If you have in a closed circuit, the ones that it's on the shade when in under shading, those panels will heat up. Moisture inspection. Moisture is critical because over time, the degradation, the temperature, the plastic materials tend to move and they tend to deform. That will allow water to go inside, whether to the modules of the bypass modules, create that corrosion. Corrosion will create a hot spot. A hot spot will just, throughout the time, will create arcing, and arcing will be, that's plenty of energy to melt the plastic and set those panels on fire. Okay, panel degradation evaluations. You have to look whether they have signs of degradation. Maybe conducting an infrared scan, that could help. Okay, no doubt about that. Evaluate the electrical installation, cables, look for arcing. Even animals, rodents, for example, they tend to bite those cables and they can have a short circuit. Access aisles, that's important. If that's because we have to think if they caught on fire, how is the fire going to be controlled? And other recommendations that we can come up with that. And before we go and understand and finish this presentation, I just want to point out some other natural hazards exposures for the photovoltaic panels. One will be windstorm, the attachment of the roof areas. There are many installations. The panels are not properly secured. And they're not properly secured. I'm not just saying throughout the roof, because the same analysis for a windstorm evaluation for a roof cover has to be conducted for a roof for a photovoltaic panel installed on the roof. Otherwise, they will blow off. They can end up in another areas or over some high voltage lines and create a short circuit, and that's going to be a huge problem. Also, if you're in a hail-prone area, your panel must be approved for extremely severe hail resistance panels. People, when they order the panels, or companies, when they order the panels, they don't specify if that's for a severe or very severe zone for hail. Okay, so that's material for other maybe future videos. And I want to thank everyone, and I invite you to check the channel for more videos in the future.